The cloud is not in the sky. You have heard that word 1,000 times. Your photos are in the cloud. Your videos are in the cloud. It sounds like something floating above you, safe, weightless, untouchable. It is not floating anywhere. It is sitting in the mud, thousands of feet under the ocean, inside a tube no thicker than a garden hose. And a single drop ship anchor, in the wrong spot, at the wrong moment, can cut the internet off for an entire country. That already happened. More than once. Somewhere in the world, it happens again this year. So here is the strange part. The system carrying almost everything you do online, every video call, every bank transfer, every message to a friend overseas, is also one of the most fragile things humans have ever built. Stay with me, because by the end of this, you will never trust the word cloud again. Here is the real question. If one lucky anchor drop can black out a country's internet, how did we end up trusting something this important to something this exposed? To answer that, you have to go back further than the internet. Back to 1850, when engineers laid the very first undersea cable, a short hop between England and France. It carried telegraph signals, simple electrical clicks standing in for letters. It worked, barely, and it proved the idea was possible. 8 years later, in 1858, someone tried something far bolder. A cable stretched across the entire Atlantic Ocean for the first time. A message that once took weeks by ship now took minutes. Queen Victoria and the American president exchanged the first messages, and for a moment the whole world seemed smaller. Then, within weeks, the cable died. The insulation was too weak, the signal too faint, and the line went silent. Critics called the whole project a fantasy. For a while, it genuinely looked like they were right. But that failure is not where this story ends. It is where the real story starts. Engineers went back, fixed the insulation, redesigned the whole system, and by 1866, a new transatlantic cable was running reliably. This time, it stuck. For the next century, cables like it carried telegraph signals, then telephone calls, using copper wire and plain electrical current. That is the picture most people still carry around in their heads. Metal wire. Electricity flowing end to end. Simple. Here is the first turn. That picture has been wrong for decades. Reveal. Modern undersea cables do not move electricity at all. They move light. Inside each cable sit thin strands of pure glass, roughly the thickness of a single human hair. Engineers fire a laser into one end. The light does not just shine straight through. Every time it hits the edge of the glass, it bounces back inward instead of escaping, over and over, for thousands of kilometers, until it reaches the other side. On the other end, that pulse of light gets converted back into the data your phone reads. Picture a hallway lined with mirrors on every wall, so long you cannot see the end of it. Shine a flashlight down that hallway at just the right angle, and the beam keeps bouncing off wall after wall after wall, never leaking out, all the way to the far end. That is exactly what is happening inside the glass. The light hits the edge, bounces back in, hits the other edge, bounces back in again, mile after mile, without ever slipping out into the ocean around it. Your message did not travel as electricity. It traveled as a beam of light, bouncing down a glass hallway under the sea. Except light fades over distance, even inside that hallway of mirrors. So engineers add repeaters, roughly every 60 miles along the cable, sitting right there on the seafloor. Each one grabs the fading light, boosts it back up, and sends it onward. A single transatlantic cable can carry dozens of these repeaters, quietly working in total darkness, powered by electricity sent down the very same cable from stations on land. And here is something almost nobody expects. A cable does not carry just one stream of data. Using a technique called wavelength division multiplexing, engineers send dozens of different colors of laser light down that same glass hallway at the same time. Each color carries its own separate stream, a video call here, a bank transfer there, all traveling side by side without ever bumping into each other. A cable no thicker than a garden hose can now move hundreds of terabits of data every second. This is not the flimsy copper wire from a century ago. This is some of the most advanced infrastructure on the planet. So if the technology is this sophisticated, here is the question worth sitting with. Why does it still break so easily? Building one of these cables starts with survey teams spending months, sometimes years, mapping the ocean floor before a single meter gets laid. Underwater mountains, deep trenches, shipping lanes, earthquake zones, all of it gets studied just to plot the safest possible route. Then a specialized cable ship loads thousands of kilometers of cable and sails out, slowly feeding it down to the seabed. Slowly is not an exaggeration. These ships move at roughly 6 miles an hour, about the pace of a light jog, for months at a time. Near the coast, the cable gets buried to protect it from anchors and fishing nets. Out in the deep ocean, it just rests on the bottom, sometimes thousands of meters down, under crushing pressure. There are more than 500 of these cables in service today, stretching over 1 million miles combined, according to the International Telecommunication Union. Laid end to end, they would wrap around the Earth more than 30 times. And despite all of that planning, all of that engineering, this system is still shockingly easy to break. A ship's anchor dragging along the bottom. A fishing trawler dropping a net in the wrong spot. Even an earthquake in the wrong place. Any one of these can snap a cable thousands of meters down instantly with no warning at all. The International Cable Protection Committee reports more than 200 of these breaks happen every single year, somewhere on the planet. When a cable snaps, traffic reroutes through whatever lines are still working. Sometimes slowing internet access for an entire country until a repair ship can locate the break and physically haul the cable back up to fix it. That can take days, sometimes weeks. Here is a twist worth pausing on. For most of the 20th century, telephone companies and national governments owned these cables. That has quietly changed. Today, companies like Google, Meta, and Microsoft are pouring billions of dollars into their own private undersea cables, just to move their own data faster between their own data centers. The same companies whose apps sit on your home screen are now in the business of laying cable across entire oceans and quietly becoming responsible for how well that fragile system holds up. That fragility is not some future worry. It is happening right now. In February of 2026, officials from more than 70 countries met in Porto, Portugal for the second International Submarine Cable Resilience Summit, organized with the International Telecommunication Union and the International Cable Protection Committee. Their goal was simple to state and hard to solve: figure out how to protect infrastructure that almost nobody can see, sitting in waters almost nobody is watching, that now carries more than 99% of the world's international internet traffic. Cables do not last forever either. Earlier this year, engineers pulled up a cable called TAT8, the very first transatlantic fiber optic cable, first switched on in 1988. It carried calls and data for 14 years before it was retired in 2002. Then sat quietly on the Atlantic seafloor for another 24 years before a recovery ship finally hauled it back up. 38 years down there in total, resting the entire time under a system most people never think about. Relevance? So why should any of this matter to you, beyond a strange piece of trivia? Because every single thing you do online that touches another country runs through this same fragile, brilliant system. Every video call to a relative overseas. Every international bank transfer. Even the artificial intelligence tools millions of people use every single day depend on this same infrastructure. Routing requests across oceans through glass and light before an answer ever appears on your screen. None of it floats through the air. All of it sinks to the bottom of the ocean, held together by careful planning, patient engineering, and, honestly, a fair amount of luck that no ship drops its anchor in the wrong place today. So the next time someone tells you their files are safe in the cloud, picture what that actually means. Not something floating above you. Something sitting in the mud, thousands of feet down, carried by a beam of light bouncing through a glass hallway thinner than your hair, one dropped anchor away from silence. Now you know why the internet can feel so solid and so fragile at the same time. It is not magic. It is a hallway of mirrors at the bottom of the sea, and the whole world is quietly betting that nobody bumps into the walls. And if a cable this thin can carry this much of the internet, wait until you find out what is actually sitting at the bottom of a black hole. Subscribe and keep finding out how the world actually works.